Hey guys, welcome back to another video. Sorry for the delay in posting, but I finally got around to filming the follow-up to the index laws one that links index laws to functions, and that's this video on exponential functions. So this is video 6 of the functions topic, and so let's just get straight into the unit overview. So in this video, I'm going to be having a look at some of the algebraic properties of exponential functions, which I've basically already outlined in the index laws video, so check that one out if you haven't seen it already. I'll be having a look at some of the features of the graph of y equals a to the x, and for translations and dilations and just transformations more generally of exponential graphs. I'll then be having a look at some contexts where you can use exponential functions to model them. The most common example, and the one that I'm going to be going over, is the radioactive decay, the half-life formula. And then finally, we'll be having a look at algebraic ways of solving exponential functions. I won't be able to go over the using technology, but hopefully that's something you go over in class. And as usual, if I miss anything in this video, make sure you do alert me and I can upload some supplementary content. Alright, cool. Thanks guys, let's get straight into it then. Alright, so when it comes to an exponential function, what it generally looks like is we have our y equals some constant a multiplied by b to the power of x. And so in this case, we have our b being the base, we have x as our exponent, and then this is a constant at the front, and that can influence vertical dilation, and as we'll see, actually also could influence translations horizontally. Something important that we should note is that for example, we have the line y equals 4 to the x. Using our index laws that we've learned, we know that 4 can be written as 2 to the 2. And using our index laws, more specifically a to the power of m to the power of n, we know that that can also be written as 2 to the power of 2x. So we can rewrite exponential functions in a bunch of different ways. And this is particularly helpful when we're trying to algebraically solve simple cases of exponential functions. For example, if we have 4 to the x equals 2 to the x, and we're trying to find the point of intersection where 4 to the x and 2 to the x intersect, we can rewrite it in terms of the same base, 2 to the power of 2x equals 2 to the x. And since we have the same base, we can then equate our exponents 2 to the x, 2x equals x, and so as a result, we know that this will only have one solution, being x equals 0. Okay? We'll go into this in a bit more detail when we are trying to solve them in a couple more complex cases with algebraic solving of exponential functions. So that's in the point 2.17. But I think we've had a good look at sort of establishing some of the properties of exponential functions here. I should note as well, actually, that you can have vertical translations as well. So these influence vertical translations. And we'll kind of have a look at what a translation looks like, what a dilation looks like in this next slide, where we have a look at the qualitative features of graphs of y equals a to the x. All right, so let's move on to those qualitative features of graphs. So we have y equals a to the x. I'm going to write that more generally, as I did before, as a times b to the x plus c. So I'm not using this a in the same sense it's being used here. That a is probably more closely represented by the b in this equation. And so what we'll see in the most simple form of, well, maybe we should actually go back to this y equals a to the x. In the most simple form of the exponential function, we have something like this. And generally, if we're looking at our graph of a function like this, it'll have some key defining points. And I'm going to go over those right now. So we have our y, we have our x, our y. One of the key things about exponentials is that any number raised to 0 other than infinity will be equal to 1. So we have 2 to the 0 will be equal to 1, we have 3 to the 0 equal to 1, and so etc., etc., up to what, 100 to the 0 equals 1, and so on and so forth. Okay? So every single exponential function, no matter what the value for a is, will always pass through the point 0, 1. So this is a key defining point. The y-intercept of any exponential function is 0, 1. Unless, that is, we have these translations, but we'll go into that in a bit of detail a bit later on. Alright, so now once we have our a value as a being greater than 1, then if we go in the positive x direction, we go stepwise in this positive x direction, what's going to happen is if we have a number greater than 1 and we raise it to steadily higher powers, what's going to happen is that my y value is going to increase exponentially. Alright? And so at our point x equals 1, we'll have increased to the point y equals a, because a to the 1 is a, and then we'll be moving to a squared, and then a cubed, which is even higher, and so we have this exponential growth. Okay? And as we go in the negative direction, if we remember our index laws, then what's going to happen is as we go in the negative direction, we're going to steadily become a smaller and smaller number as a to the x tends towards a larger and larger number. Because it's a negative number, we're going to have this fraction, and so it's going to be 1 divided by a steadily larger and larger number. And so as a result, as we tend towards negative infinity, y is beginning to tend towards 0. So as x tends towards negative infinity for our basic exponential function, our y is going to tend towards 0 from the positive side. And so as a result, what we have here is a horizontal asymptote at y equals 0. Okay? If we change our a value and we have a larger value of a, what's going to happen is let's say we have a line y equals b to the power of x, where b is going to be larger than a, then what happens is at 1 we have y equals b, which is larger than a, and so we have this, and then again at 2 we're going to increase by an even greater amount, and so we have a steeper exponential growth, but it will still pass through the point 0, 1. And then as x tends towards negative infinity, we're going to have 1 divided by a larger number raised to steadily greater values of x. And so as a result, our red function is actually going to approach 0 faster than our green function. Oh, that should be in red. So it'll also asymptote at y equals 0, but it'll get there faster, and that's what you can see here. Okay, so it's slightly below the green function. Okay, cool. So that is those are the two key functions there. The two key characteristics of exponential graphs. We have our horizontal asymptote, and we pass through the point 0, 1. All right. Now, if we look at translations of graphs, so y equals ax, a to the x plus b, or y equals a to the x minus c. Okay, let's have a look at that. I'll just rub this out so we have a bit more space. And so if we remember and we recall, our basic exponential function will be passing through the point 0, 1, and it will have a horizontal asymptote at y equals 0. And so it looks kind of like this. And I'm going to just represent it like that. And so this is the point 0, 1. Now let's say we wanted to graph the line, the exponential function y equals a to the x plus 1. Okay? What happens then is every single point on this curve is going to be shifted up 1 point. Okay? And so what happens to our y-intercept is we shift that up to the point 2. And similarly, at this point 1, whatever that value is, gets shifted up 1 point here. And so as a result, what we see happen with a vertical translation is that every single y value is increased by 1. And so as a result, what actually happens is that our horizontal asymptote, which was previously y equals 0, is now y equals 1. Okay? So as x tends towards negative infinity, we have a 1 over a really, really large number, and so this is tending towards 0. And so as this term tends towards 0, we only have this 1 left. And so as a result, we have this horizontal asymptote at y equals 1. Okay? And so if we have a more general function, and if we generalize this into the form y equals a to the x plus c, then what's going to happen here is that we have a y-intercept equal to 1 plus c, okay, because 1 is the normal one, and then c is the vertical translation. And then we also will have a horizontal asymptote equal to c, because our initial asymptote is 0, and we've translated that horizontal asymptote c units in the positive y direction, y, x. Okay? Cool, I think that's mainly it on that. Let's have a look at horizontal translations then. And I'm going to let a be 2 in this case, just to illustrate one specific case that arises here. Okay, let's just see if we can rub this out. Eesh. Unfortunately, that will have to stay. Okay. All right, so now in the case of a horizontal asymptote, let's say we have our line, this is our line y equals a to the x, and then we have a different line where we have a look at y equals a to the x minus d. I'm not going to write c because I've already written a c here. So x minus d. All right, so what happens here, what this refers to is a horizontal translation, d units to the right. And notice that we have a minus here. So if we have x plus 3, so for example 2 to the x plus 3, that'll be a graph of y equals 2 to the x shifted 3 units in the negative direction, towards the left. Okay, this is the positive x direction, and this is the negative x direction. And the reason why that's the case is because we'll have minus 3. And so we have 3 units in the negative direction. Okay? So if we have, for example, let's make this graph y equals 2 to the x. Then we know that we have a intercept at 0, 1. At the x coordinate 1, oh, this is not a great graph. Let's see if we can draw this a bit better. At the point here, we trace at the point 1, we are y equals 2. 2 to the 1 is 2. At the point 2, we go up to 4, because 2 squared is 4. And at 3, as you might have guessed, we have y equals 8. Now, if we are graphing, for example, y equals, let's say, y equals 2 to the x minus 2. Okay? What happens here is everything is being shifted 2 units to the right. And so what was previously at 1 is now at 3. So this point 2 is now at 3 here. This point 2 is now at 4. Oh, these coordinates are not great, are they? So at 4, we are equal to 4, because we've got that right shift of 2 units. What was previously at 0, 1 is now at 2, 1. And then so when we have x equals 0, our y value will be 2 to the 0 minus 2, which is 2 to the minus 2, which is 1/4, or 1 over 2 squared. And so as a result, at our y-intercept, we have something that looks like this. And then this will also have a horizontal asymptote at y equals 0. Okay. Something I should also note is this actually has a direct tie to our value a here. Not this a, but this a here. Sorry, it's a bit confusing with the variables I've used. But, so, if we write 2 to the x minus 2, using our index law, a to the b plus d, we know that's equal to a to the b times a to the d. And similarly, a to the b minus d is equal to a to the b over a to the d. And so if we have a look at this, x minus 2, that's going to be equal to 2 to the x divided by 2 to the 2, which is equal to 1/4 times 2 to the x. And if we have our original function and we multiply it by 1/4, what's happening here is that we've introduced a vertical dilation by a scale factor of 1/4, or 0.25. Okay? And so there is a direct correlation and a direct tie between vertical dilations and horizontal translations in exponential functions, in that they are the exact same thing. Alright, I think that's the main thing. And I would advise that you practice this as much as you possibly can, because yes, these can get a bit tricky to graph. When it comes to exponential functions, unlike, for example, quadratics, where you have to solve things and try to figure out where the roots are and everything, when it comes to exponential functions, generally what you're doing to graph them is you're substituting values for x and seeing what the y values are, and then you're just kind of connecting up the points in a smooth curve. Okay, so when you're graphing an exponential function as well, I should point out that generally you'll have 1 mark awarded to the shape, the curve. Oh, here's the curve, the shape. You'll have 1 mark awarded to the y-intercept normally. You'll have 1 mark awarded to horizontal asymptote, and then sometimes they can actually give you a mark for some random point to ensure that you've actually drawn the correct exponential function, that it isn't something like it looks like this and then you've just kind of gone like that. Okay, so they'll put some random point to make sure that you're actually drawing the right exponential function. So it's actually this function and you're not drawing something random like this, even though it has the same y-intercept and the same horizontal asymptote. If that makes sense, hopefully. If it doesn't, leave a comment in the comment section. Okay. Alright, some contexts where we look at using exponential functions. I think one of the most common things that you see is the half-life equation, and that's generally related to exponential decay. And so kind of what a half-life is and radioactive decay is you've got a radioactive compound, and after a certain amount of time known as the half-life of that compound, the mass of that compound has halved in size, or the number of particles present in that compound have halved in size. And so what that kind of looks like is, like, we have a look at the number of particles after a certain amount of time will be equal to the number of particles at time 0 plus, multiplied by 1/2 to the power of t on t to the 1/2. And so here t to the 1/2 is the half-life, so that's that period of time that it takes for the radioactive compound to have halved in mass or number, and then t is the amount of time that's elapsed. And so if you look at this and you see that your time elapsed divided by your half-life, what that represents is the number of half-lives. The number of half-lives. Half-lives, half-lives, half-lives. I don't know. Half-lives, half-lives. Anyway. Okay, so after a certain number of half-lives have elapsed, you will have halved the number of particles that were initially present. So if the time elapsed is equal to 1 half-life, then you will have 1/2 to the power of 1. And so the amount you had initially will have halved, right? And so after the time elapsed being 1/2 life, you'll have half the amount you initially had left over. I hope that's not too confusing. After 2 half-lives have elapsed, you'll have 1/4 of the amount you initially had. And so that continues on and on and on and on. And this is what that kind of looks like, this equation. And so, for example, if we had, let's say we had 100 grams of a certain substance at time 0, and then the half-life of this is the T1/2 is equal to, let's say, 1 day, okay, just for the sake of the argument. And then we can graph this with a y-axis being n and our x-axis being t, given that t is our independent variable because the amount of time that's elapsed influences how much mass we have remaining. And so at time equals 0, we have 0 time elapsed, so we have 1/2 to the power of 0, which is 1. And so it'll be 100 times 1, and that makes sense because at time 0 we have 100 grams of whatever we had at the start, right? So now if we look at time elapsing in the positive direction, okay, if we have let's say we have one day has elapsed now, what happens is we have 1/2 to the power of 1 divided by 1. And so we have 1/2 times 100. So after 1 day, we will have half the amount we initially had remaining. And so this is after 1 day. And so this is 50 grams, this is 100 grams. After 2 days, we'll be at 25. 3 days, 12.5, and so on and so forth. So as a result, we have an exponential decay that kind of looks like this. And generally, we're not going to graph this point here, even though it does exist, because we're only starting to track at time equals 0. You don't really have negative time, right? So thinking about the contextual relevance of what you're kind of solving here is really important. And if we look at 1/2, note also that we can write 1/2 is the same as 2 to the negative 1. And so if we're looking at a graph like this, we could also equally write nt is equal to n0 times 2 to the negative t over t1/2. Right? And more generally, if we have graphs of y equals a to the negative x, this is something I should have mentioned earlier, sorry. If we have a to the negative x, in this case, as a tends towards infinity, we have y tending towards 0. As x tends towards positive infinity, y tends towards 0 in the positive direction. As x tends towards negative infinity, y tends towards positive infinity. Because the negatives cancel out, and as a result, you have your curve going upwards. And what happens is, this kind of is like a reflection, where your normal graph kind of looks like this. Y equals a to the x looks like this. Y equals a to the negative x will look something like this one. Okay? All right. Now let's just quickly take a look at solving some exponential functions, and then we'll call it quits. I've gone over this quite quickly again, but make sure you're asking questions in the comment section so I can go over that. Let's say you have something like 2 to the x plus 2 to the x equals 2 to the 2x plus 3. Or maybe we could even have something like make it even more complex. How do we go about solving something like this? The key thing is identifying what is the lowest base I can express this to. We know that 4 can be expressed as as 2 to the power of something, right? We know that 4 can be expressed as 2 squared. And so as a result, our lowest base, where we can match all the bases up, will be 2. We also see that we've got 2 of these. So one box here plus another box here. And so we can equally write that as 2 times 4 to the x equals 2 to the 2x plus 3. And so using our exponential laws, we have 2 times 2 to the 2x equals 2 to the 2x plus 3. And so since we have 2 to the 1 times 2 to the 2x, we have 2 to the 2x plus 1 equals 2 to the 2x plus 3. And now that we have the same base, we can equate the two values. 2x plus 1 equals 2x plus 3. And actually, I've just realized that this is actually impossible to solve, so sorry about that. Yeah, all right, but when you have a when you see a Sadler textbook question, they will obviously be possible to solve, and this is the sort of process that you go through when you're trying to solve the equations. Okay, cool. Thank you for watching this one. Make sure you're subscribing so you don't miss any new videos. Comment if you don't understand a concept or I've missed anything. As usual, I will put the link or the textbook reference from Sadler in the description of this video. And just wanted to let you guys know that the next video for this series releases on the 31st of October, so in 2 days. And I'll be back to posting regularly again. Thanks, guys.